Hello everyone, my name is David Chen, a first-year PhD student studying in University of Illinois, advised by Professor Rakesh Kumar. I'll be introducing our work on wafer-scale network switches, where I show that wafer-scale integration can increase the radix of today's switches by 32x. Network switches are ubiquitous in today's computing infrastructure. They can be found in data centers such as this one from Meta, which uses thousands of switches to interconnect all servers across 6 buildings. They can be found in HPC systems such as this Cray Sashta supercomputer, where they are used to interconnect all compute nodes. They can also be found in GPU clusters such as this NVIDIA DGX SuperPod, where InfiniBand switches are used for CPU communication, and NVLink switches are used for GPU communication. As such, network switches are a critical component of modern computing infrastructure. The architecture of a switch is often characterized by its radix. Radix of a switch is defined as the number of bidirectional ports on the switch. A high radix is critical to reducing latency, cost, power, and volume, as well as improving the scale of the network. Consider the following example. Suppose I have a switch with radix of 4. I can use this switch to connect 4 servers. Now let's say I want to connect 8 servers. I now need 6 switches to connect them. However, if I have a switch with radix of 8, I would only need a single switch to connect to all 8 servers. This reduces latency of a communication between servers, as the communication is 1 hop instead of 3 hops. This reduces cost because we reduce the number of cables and transceivers needed by half. Having fewer switches also reduces power and volume. So having high radix switches is beneficial, but scaling up the radix of a switch is very challenging. To increase the radix, the number of I/O pins must increase to accommodate the I/O pins of additional ports. Unfortunately, I/O pitches have scaled poorly over the years. Figure on the right shows the relative scaling of I/O pin densities over the last 2 decades. For BGA packaging, I/O pin densities have scaled only by 8x in the last 20 years. For LGA, it is even worse. I/O pin densities have scaled only by 2.3x in the last 20. So if I/O density is not scaling well, we will need to increase the size of the chip to accommodate more ports in order to increase the radix. Another critical reason why increasing the size of the chip is necessary is that die sizes of crossbar based switches scale quadratically with their radix, shown in the figure. Each additional port means a new row and column to the crossbar. Unfortunately, chip sizes scale poorly due to yield concerns and radical limits. As a result, the maximum radix achieved scales much slower compared to the aggregate switching bandwidth of a switch. While the switching bandwidth has grown by 50x in the last 10 years, the maximum radix of a switch has only grown by 5x. Therefore, a radical solution is needed to significantly increase the radix. We propose using a chiplet-based wafer-scale integration technique to construct a very high radix switch that is as large as a wafer. We start with a single substrate chiplet, or SSC for short. It is an existing switch die with some radix. We take a large wafer-scale substrate and bond many SSCs onto it. We connect them with interconnect on the substrate. I/O signals can be supplied either via periphery I/O chiplets or area I/O from the back or front of the die. As a specific example, here we have a 3x3 wafer scale switch. The SSCs are connected via chip-to-chip link on the substrate. The SSCs are connected to I/O chiplets via chip-to-I/O link also on the substrate. As the chip-to-chip link is passive, it is not long range. So SSC has pass-through on-chip links on them as well. Optical fiber directly enters the I/O chiplets. Power is delivered through the back, and the cold plate sits on the top of the SSCs. Substrate chiplet, or SSEs, can be connected in different topologies such as mesh, torus, cube, and etc. to achieve the desired performance and cost trade-offs. Different logical network topologies can be mapped to a physical network of SSEs. In this work, we chose to map the cross network to the 2D mesh-connected SSEs. We chose cross since it is non-blocking, fault-tolerant, and offers high bisectional bandwidth. We chose to use 2D mesh physical topology as it reduces complexity of manufacturing, placement, and routing. I will show the mapping operation in an example. Here, 0 to 4 has a logical connection that can be mapped to the physical network very easily because 0 and 4 are adjacent. 0 to 5 can be mapped as 0 to 1, 1 to 5. Similarly, 0 to 6 can be mapped as 0 to 1, 1 to 2, and 2 to 6. Our proposal promises large radix benefits if we just look at how many SSE dies could be fit on the substrate. Here, x-axes show the bandwidth per port in gigabits per second, and the y-axis show the maximum achievable radix. At 200 gigabits per second, we could achieve radix of 8192, 4096, and 1024 for 300, 200, and 100 millimeter substrate, respectively. 8192 is 32x higher radix than state-of-the-art, a radix 256 Tomahawk 5 switching ASIC, or TH5. However, the reality is much more complicated. To achieve the promise of 32x higher radix, we need 3000 gigabits per second per millimeter of external bandwidth density, 6400 gigabits per second per millimeter of internal bandwidth density. If we assume SerDes-based external connectivity, we hit only 512 gigabits per second per millimeter of external bandwidth density. So we are severely bottlenecked by I/O bandwidth, shown by these outer links in red. With optical I/O, we could achieve 3200 gigabits per second per millimeter of external bandwidth density, but now we are bottlenecked by internal bandwidth instead, shown by these inner links in red. For a 4 micron internal I/O pitch, 4 layers of interconnect, and internal links running at 3.2 gigahertz, we have 3200 gigabits per second per millimeter of internal bandwidth density on the substrate. This discrepancy between requirement and availability reduces the achievable radix. We see only 8x benefit from Waferscale integration instead of the promised 32x. Even if we forget about the bandwidth limitation, a Waferscale network switch draws excessive power. The figure plots the required power for various radix that we achieve using SerDes, area I/O, and optical I/O at 300 mm substrate. We see that at 8192 radix, the system uses 63 kilowatt. This is too high even for liquid cooling. We can only liquid cool the 2048 radix system. The situation becomes worse if we consider air cooling only. To address the internal bandwidth problem, we propose the use of deradixing. Using lower radix SSEs that have the same die size, we could alleviate internal bandwidth congestion. As we reduce the SSE radix from 256 to 128, we used twice the number of SSEs to achieve the same system-wide radix of 4096. However, because each SSE has half the required internal bandwidth as before, the bandwidth utilization went from over 150% to just 90%. So we achieve 8x benefits over baseline without deradixing, but 16x with deradixing. To address the power consumption problem, we propose to use heterogeneous SSE with different radixes. We observe that we could use 2 SSEs with half radix as a leaf node without changing the overall radix. We also know that power varies quadratically with radix, so we are able to reduce the overall power when compared to the homogeneous SSD system without affecting the system radix. Here, the x-axis is the radix of leaf SSDs, and the y-axis is total power. While maintaining the same system-wide radix, the heterogeneity optimization allows us to cool the 300mm system using liquid cooling with leaf SSDs as 1/4 of the original radix. So this 30% reduction in power, which allows a radix of 8192 at 200 Gbps switch for the same power budget. Such switch could be used to drastically reduce costs in a hyperscale data center, to build a single switch on-premise data center, or to construct a massive singular GPU. In all these use cases, we see significant reduction in number of switches, volume, number of cables and transceivers, hop counts, compared to baselines with conventional network switches. In summary, high radix is critical to reducing latency, cost, power, and volume, as well as improving scale. However, radix scaling is extremely slow, so radical solutions are needed for a significant radix increase. We propose a Waferscale network switch, which promises 32x higher radix. However, the achievable radix greatly limited by bandwidth and power concerns. We propose optimization such as deradixing and heterogeneity to alleviate these concerns. This optimization can enable a radix of 8192 200 Gbps Waferscale network switch. It opens up novel use cases such as single switch low-cost data centers or massive singular GPU. Overall, this is a ripe and fruitful area of research. Thank you for listening.